In this video, I'm going to talk about unitless measures of linear association that might come up in a linear regression context. Unitless measures of association are also known as effect sizes, but I don't always use the term effect size. I will use the term effect size sometimes. It's very commonly used and we all kind of have gotten used to saying it. But when I'm thinking about it, I tend to try to avoid that term because I don't want to imply that measures of association are inherently about cause and effect relationships. You can use measures of association that are standardized even for cases where you don't know that the relationship in question is causal. And in order to talk about effect sizes, I'm going to be working with this section of the regressiondemos.r code file. But before I walk through this portion of the code file, I want to show some slides illustrating some different kinds of effect sizes that I'll then show in practical terms in our code. So let's talk a little bit about some kinds of unitless measures of linear association or effect size for regression models. And first I want to remind you what standardizing a variable means. This is also known as z-scoring a variable, so I'm using a subscript z to represent it here. The standardized version of a variable y, which I'm calling here y sub z, is equal to y minus its own mean divided by its own standard deviation. And the result of that operation is a variable that has a mean of 0 and a standard deviation of 1. A regular or unstandardized regression slope, the kinds of slopes that we've been talking about so far, is defined by this equation that you should already be familiar with. Here with just 3 predictors as an example, but you could have any number of predictors. These slopes, b0, b1, b2, and b3, come from minimizing the sum of squared residuals e given the observed values of y, x1, x2, and x3 in their original units. The standardized regression slopes are the result of applying the same least squares operation with standardized versions of all of the variables in the model. So we have a standardized version of the response variable and standardized versions of each of the 3 predictor variables, which I'm here denoting x sub 1 z, x sub 2 z, and x sub 3 z. All 4 of these variables have been z-scored, and then we fit a model where we minimize the sum of squared residuals. And we get standardized slopes for each of the predictors, which here I'm denoting those standardized slopes with b star. That's one of the common ways of doing it. People also use b prime with a little tick after the b, like an apostrophe. And sometimes people also use the Greek letter beta, especially if they're SPSS users, because SPSS uses beta to represent this value. When we fit this model, the intercept, which here I'm denoting b sub 0 star, is 0. So you don't actually need to show it, but I'm showing it here for the sake of similarity with the general regression formula, because what we are doing is still estimating these parameters by minimizing the sum of squared residuals just the way that we normally do. Standardizing all of the predictors and the response variable in order to get standardized slopes is the most common way of standardizing a regression slope. But there are other options. There are other values that are called standardized slopes. So you probably should not assume that the term standardized slope is a term with a universal definition. It's reasonable to explain that you're standardizing the slopes by standardizing all predictors in the response variable. And you might sometimes think about other options. For example, if you have a binary predictor, you might consider a version of a standardized slope that does not z-score the binary predictor. But most of the time, when I talk about standardized slopes, I'm going to be talking about this default approach that standardizes absolutely everything and then defines b star as the least squares slope that results from standardizing absolutely everything. Another way to get this kind of b star, this standardized slope, is by taking the unstandardized slope and rescaling it by the standard deviations of the relevant variables. So for example, in this case, if I have a model with 3 predictors here, and I have b star sub 1 that I got from redoing the least squares regression after z-scoring all of my predictors, that b star sub 1 would be exactly the same as if I took the original b1, the unstandardized slope from regression model with these values in their original units, and I multiplied it by the standard deviation of its predictor, the standard deviation of x1, and then divided it by the standard deviation of the response variable y. So this is often a faster way to get the standardized slope. If there's only one predictor, x1, then the standardized slope is the same as the regular old correlation coefficient r, the Pearson correlation between x1 and y. This correlation is an example of a unitless measure of linear association, a standardized effect size, because it eliminates the units of x and y and just tells you how strongly they are associated in terms of standard deviations. But even in a context with more than one predictor, once we've standardized the slope, it can be useful as a unitless measure of linear association, describing an association in terms of standard deviations instead of the original units of the variables. But there are other options too for unitless measures of linear association when we have multiple predictors. When we just have one predictor, the regular old Pearson correlation is the default and probably the only one that you'll ever think about. And it's equivalent to the standardized slope and also equivalent to these other options that we're talking about. But as soon as you add other predictors in there, the situation gets more complicated and you have more options to choose from for how to define a unitless measure of association. So besides the standardized slope that we've already talked about, we have the partial correlation and the semi-partial correlation that I'm going to talk about today. So here, let's imagine a regression model with two predictors, x1 and x2. And I've got slopes b1 and b2 that correspond to them, and a residual e that represents the discrepancy between the fitted values from this portion of the regression equation and the actual observed values of y. That residual e is a measure of how wrong this model is, how much of the variability in y is left over after we account for both x1 and x2. Now let's imagine two other regression models, simpler ones. The notation here is kind of arbitrary, so don't take this b0.1 as something technical. I've made the slopes and intercepts here show up in gray because they don't actually matter for what I'm about to talk about. We don't care about them. What's important is that we can imagine a regression model that predicts y based on x2 alone, without x1. That's just a simple linear regression model in this case. And we can also imagine a regression model that predicts x1 based on x2 alone. x1 was a predictor variable up here, but there's no reason we can't treat it as a response variable down here. What we actually care about from these two simpler models that we're imagining for a moment is their residuals. So e sub y here represents how much of the variability in y would be left over if we modeled it based on only x2. So after accounting for x2, how much of y's variability is left? And e sub x1 here represents the residual from this regression model, how much of the variability in x1 is left over after accounting for x2. The partial correlation between y and x1, adjusting for x2, is equal to the correlation between e sub y and e sub x1, as shown on the screen here. In other words, partial correlation, adjusting for some other variables, is equivalent to the correlation between residuals of regression models that use those other variables as predictors. The correlation between how much of y is left over after accounting for x2 and how much of x1 is left over after accounting for x2. That's the partial correlation between x1 and y. The semi-partial correlation between y and x1 adjusting for x2 is the correlation between the actual observed values of y and the residual from this x1 model, e sub x1. In other words, it's a correlation between how much of x is left over, how much of x1 is left over after adjusting for x2, and y itself, not the residual of y. That's the difference between the partial correlation and the semi-partial correlation. The partial correlation uses the residual of y, and the semi-partial correlation uses y itself, but the residual of x. Either way, the result is a unitless measure of linear association. The units are standard deviations. The semi-partial correlation has another name. It's also known as the part correlation, but please don't ever call it that. I honestly think that's a ridiculously confusing name, and I would prefer that it didn't exist. So on the same slide, a comparison between the partial correlation and semi-partial correlation. The partial correlation between x and y is the regular old Pearson correlation, but not between x and y themselves. It's the regular old Pearson correlation between the residuals from a model with y being predicted by all the other predictors except x, and the residuals from a model with x being predicted by the other predictors besides itself. I'm using the tilde here as shorthand for fitting a linear regression model based on those variables and borrowing it from the R formula syntax. The semi-partial correlation between x and y, adjusting for a bunch of other variables, is the regular Pearson correlation, but again, not between x and y directly. It's the regular Pearson correlation between y itself and the residuals from a model predicting x based on all the other predictors besides x. The partial correlation will always be higher than the semi-partial correlation because it takes out some of the unexplained variance from y, this part, before computing the correlation, whereas the semi-partial correlation just uses all of the variance in y, and so it will be a smaller number. But both of these correlations are restricted to be between -1 and 1, just like a regular Pearson correlation. The semi-partial correlation is maybe a better bet if you're reporting an effect size for multiple linear regression model, because it somewhat more closely resembles what's going on in the model, although not everyone 100% agrees on that point. They're both reasonable effect size measures. We can give another interpretation of the semi-partial correlation. The semi-partial correlation between x and y is the square root of the amount by which the r² value from the regression model increases when x is added to the model. So if you have a model that has x and some other predictors and y is the response variable, you can imagine taking x out of the model and getting the r², and adding x back in the model and getting the r² after that point. And if you take the amount that the r² changes and take the square root of that amount, you get the semi-partial correlation. So another way of thinking about the semi-partial correlation is that it's the variance uniquely explained by x. And a related interpretation of the partial correlation is that it's the semi-partial correlation itself divided by 1 minus the r² value from a model that predicts y based on the other predictors besides x. It's a variation on the semi-partial correlation that has been scaled upward by dividing it by the fraction of variance that would have remained unexplained before adding x to the model. So summarizing these three options we have as unitless measures of linear association, or standardized effect sizes that you can use for multiple linear regression models. I talked about the standardized slope represented b star, b prime, or beta, which is the slope in units of standard deviations. I talked about the partial correlation, which is the correlation between the residuals of both variables. And I talked about the semi-partial correlation, which I think is easiest to understand as the square root of the proportion of variance in the response that's uniquely explained by the predictor.